This is a new section that I did not do last year. It's called Proof by Strong Induction. And the first thing I want to mention about it is that it's a misnomer. It's not really stronger. It's just different. So don't think that it's like an actually, that you can know, it's just somehow better than the other one. Both accomplish what you want, both prove, but this is just a different variant. So the variant, if you just kind of remember that induction proof style, you look to see if P of k is true, that implies P of k plus 1 is true. And I guess the weak part about induction is that it looks back only one step. This is very good for things that are just simply sequential. But we saw a couple of times where it actually was kind of difficult to use because we might want to look back more than one step. So strong induction does just that. It looks back more than just one step. And it has a huge leap in its hypothesis that some might have a problem with. Here's the strong induction thing. We let P of n be a condition, or a statement. And that's defined over all integers n. And the like before, you always look at a base case and you have an inductive hypothesis. The formal definition is if P of a plus 1, all the way up to P of b are true for integers a less than or equal to b, and a equals b is the actual regular induction. But if there's more than one, we can do it. We want to see if for any integer k greater than b, if all the pi's are true for a less than or equal to I less than k. And if that's so, then P of k is true. Now, that's a very mathematical way to describe it. I'm going to kind of describe it a little bit more simply as we move through some examples, and you'll hopefully get the feel for how this works. So let's just dive into one very simple example. We're going to do 3 of these. And these are a little bit more writing than we've done before, but the first one is divisibility by a prime. This is just going to establish something that's inherently obvious, but we're going to use the strong induction case to show. The thing we're going to prove is that every integer greater than 1 is divisible by a prime number. And I'm going to organize this by having a base case, and a hypothesis, and then a proof. So our base case is 2. 2 is an integer greater than 1, and we know that 2 is divisible by 2. That's a trivial case. Our hypothesis is that every integer up to k is divisible by a prime. That is, again, a huge inductive hypothesis, because rather than just saying k is divisible by a prime, we're saying every integer up to k is divisible by a prime. And we have to do that because when we look at k, either k is prime, in which case it's divisible by itself, or it can be factored as integers that are less than k. Which, by our inductive hypothesis, are each divisible by a prime. And that's the end of the proof. Now, the question is, why do we have to use strong induction? And ultimately is because we're factoring composite numbers And when factoring composite numbers, it yields numbers that are less than k minus 1, less than one step before. So we have to look at all the possibilities before that when doing this. So that's a simple example of strong induction. Let's go a little bit more complicated, a little bit more of an interesting one. This next one's called the binary representation theorem. And sometimes I annoy the hell out of my Algebra 1 and Algebra 2 kids by numbering in binary, just to show them there is math outside of that which their limited brains can conceive of. I kid. Every positive integer n can be expressed as n equals some constant r, c sub r, times 2 to the r, plus c sub r minus 1 times 2 to the r minus 1, plus all the way to a c2 times 2 squared, plus c1 times 2, and then plus a c0. And this is true where each c is 0 or 1. So basically 0 or 1 times each possible power of 2, and you can get every single possible number. That's the binary representation theorem. It says every number can be expressed in binary. Your basis case of n equals 1 means just that c sub 0 is 1 and all the rest of them are zeros. Your inductive hypothesis is to assume that every integer up to k has a binary representation. Yep. Every integer up to k has a binary representation. So now we're going to prove that if that's true, then k is going to happen. So if k is even, we know that k over 2, which is an integer less than k, has a binary representation. And we know that that means that k over 2 is equal to c sub r 2 to the r plus c sub r minus 1 2 to the r minus 1 plus c sub 2 2 squared plus c sub 1 2 plus c sub 0. And as you might imagine, if we just solve for k, I've got k is equal to c sub r 2 to the r plus 1 plus c sub r minus 1 2 to the r plus c sub 2 2 to the third plus c sub 1 2 squared plus c sub 0 times 2. And I found it for, so that's easy. If k is even, we just, again, can get a binary representation for k. If k is odd, then k plus 1 over 2 is a way to represent the odd number. Or sorry, k minus 1 over 2. Bad. Actually, it doesn't matter, but I'll do k minus 1 because it'll be cleaner. Oops. We got c sub r 2 to the r plus c sub r minus 1 2 to the r minus 1. And I know that that's true because, again, k minus 1 over 2 is definitely a number contained in our inductive hypothesis. So if I solve for k, I get c sub r 2 to the r plus 1 plus c sub r minus 1 2 to the r plus c sub 2 2 cubed plus c1 2 squared plus c sub 0 2 and then plus 1. So my last constant is 1. And it's either an odd, so that's true. And the question of why SI here, again, it's because k over 2 or k minus 1 over 2 were much less than k minus 1, which is what we would have used with regular induction. Last problem. This is a problem variant called properties of a sequence. We've seen a few of these before. Now we're going to prove a little bit more with strong induction. So we're going to consider the sequence A1, A2, A3, where A1 is 1, I need a little more space here. A2 is 2, A2 is 2, A3 is 3, and AN is AN minus 1 plus N minus 2 plus AN minus 3. It's the sum of the three previous terms. So I have to define the first three terms, and then I've got it. So as you imagine, A4 is 6. And the proof is we're going to show that A sub n is less than 2 to the n. And our basis case is that A4 is equal to A1 plus A2 plus A3 equals 1 plus 2 plus 3, or 6, and that is in fact less than 2 to the 4th, or 16. So our hypothesis is that we assume A sub I is less than 2 to the I for I equals 5, 6, 7, all the way up to k minus 1. So we're assuming this is true for all the I values. Assuming this is true for all the I values up to k minus 1. Our proof is to show A sub k is less than 2 to the k. So I got A sub k, which is equal to A sub k minus 1 plus A sub k minus 2 plus A sub k minus 3. And I know that each of those, each individual one of these, is part of its own inductive, or part of that inductive hypothesis. So A to the k minus 1 has to be less than 2 to the k minus 1. And A to the k minus 2 has to be less than 2 to the k minus 2. And A sub k to 3 has to be less than 2 to the k minus 3. And if I factor that, a 2 to the k minus 3 out, which is the lowest of the three, I should get 2 squared plus 2 plus 1. And add that up. I should make this an equal. Make that an equal. Add these up, I get 7 times 2 to the k minus 3. Okay, so what? Well, what I'm actually trying to show is this 2 to the k. I want to see where that compares to 2 to the k, and if that's equal to 2 to the k or that's less than 2 to the k, then that's okay. Well, I can actually show that this is less than 2 to the k because, I'll do this. 2 to the k is really 2 to the k minus 3 times 2 cubed. And clearly 2 cubed, which is 8, is equal to 2 to the third times 2 to the k minus 3, or 2 to the k. So, shown it. Question here of YSI. And the reason is because the inductive hypothesis needed to apply to k minus 1, k minus 2, and k minus 3. So, that's it.